Welcome back to the next video. Now we're going to see a small example that shows us how to actually diagonalize a matrix and how to recognize whether it's diagonalizable in the first place. So as our example, we will be using the matrix A that looks like this. This is 0, 1, minus 1, 0. And you hopefully recognize this. We've already seen that matrix. We've computed the characteristic polynomial of that. But let's do this once more. So PA of lambda is the determinant of minus lambda 1 minus 1 minus lambda. And that is just lambda squared plus 1. So we've seen that in this example of a matrix that has no real eigenvalues, but of course it has complex eigenvalues. So lambda squared plus 1, we can easily write this as lambda squared minus I squared. And that means this is the same as lambda minus I, lambda plus I. So we don't have any real eigenvalues, but we do have two complex eigenvalues. Lambda 1 is I, and lambda 2 is minus I. What does this mean for multiplicities? Well, for lambda 1 equals I, the algebraic multiplicity is, well, 1, obviously, because the linear factor in the characteristic polynomial here appears once. Yeah, so this is where this 1 comes from. And the same is true for lambda 2. So let's write this down right away. Again, the algebraic multiplicity is 1. What about the geometric multiplicities? Well, if the algebraic multiplicity of an eigenvalue is 1, then the geometric multiplicity is also 1. There needs to be at least one eigenvector, so we get at least 1. And there is the multiplicity is at most the algebraic, so at least 1 and at most 1. That means it has to be equal to 1. Okay. So in this case, the geometric multiplicity is then also 1, and same thing for the other eigenvalue. Okay, that means for both eigenvalues, algebraic and geometric multiplicity agree, and we already know that this matrix can be diagonalized. It is diagonalizable over C. We do need complex eigenvalues, but other than that, it's fine. Okay, so let's proceed to actually computing the eigenvectors. And that's part 2 then. Let's compute these eigenvectors here. Again, we'll start with lambda 1 equals I. And we consider the matrix A minus I times the identity matrix. So remember the matrix A, that was 0, 1, minus 1, 0. And now we want to subtract the identity matrix times I. So that's minus I here and minus I here. Okay, we need to compute the kernel of that matrix. That is the eigenspace. So basically we need to solve the linear system matrix times x equals 0. So what we do here is we add I times the first row to the second one. Okay, that does not change the first row. And the second one, well, becomes the second row. So we have I times minus I, that is minus I squared, that is plus 1. And minus 1 plus 1 is 0, that's why we did that. And in the second column, we get I minus I, that's also 0, so all's fine. We actually get one eigenvector. So the eigenspace of A for the eigenvalue I is spanned by, let's see, we choose 1 for the first coordinate, and if we do that, we have to choose I for the second. Then the first row times this vector becomes 0, and the second row is 0 anyway. Okay, so that's a basis for our eigenspace here. Basis for this eigenspace. Okay, so that is going to be the first vector for our eigenvector basis for A. Then let's do lambda 2 minus I. That's of course similar. This time we look at A minus I E2. Be sure to not confuse the signs. So what we do is actually A plus I E2. And that is I 1 minus 1 and I. So this time, to compute the kernel, we have to subtract I times the first row from the second one. And what we get is first row stays, second one. So I times minus I is plus 1, minus 1 is 0, and minus I plus I is also 0. That works out nicely. So that kernel, the eigenspace, we can again come up with a vector that spans that. We just set the first coordinate at 1 arbitrarily, and if we do that, well, we have 1 times I here. So we get I, the second one, 1 times whatever needs to be there to be 0. So we need to put a minus I there. So this vector times the first row is actually 0, and for the second row it's 0 anyway. Okay, and again, this is of course a basis for the eigenspace, this time for the eigenvalue minus I. Okay, so here's our eigenvector basis. Eigenvector basis is 1 I and 1 minus I. And note that this does include vectors which have complex components. Okay, that gives us our transformation matrix. We just get the transformation matrix by using the eigenvector basis vectors as columns. So S is 1 I in the first column, 1 minus I in the second column, or vice versa. And if you then compute the transformation S to the minus 1 AS, you get I 0, 0, minus I. That's the diagonal form that we want here. Okay, that concludes this example, and in the next video we're going to see how to apply this theory to systems of linear differential equations, so you can actually solve at least some instances of these equations. Thank you.